Hello, for today's presentation, so we'll be discussing application of first order differential equations for growth and decay problems. Okay, so for growth and decay, so there are various engineering problems, okay, so which involves growth and decay. Like for example, if I want to determine how old, okay, a given artifact is, so we can solve that one so by using the principle of carbon. Okay, so we're in carbon decays over a certain period of time, so particularly carbon 14, that the half-life, okay, of the carbon is known, and so from there, so we'll be able to determine so what would be the approximate age of a certain artifact. And we can use as well this principle so in predicting future values, so such as determining what would be the future population of the Philippines. So let's say that for a certain period of time, the population is known. So let's say currently there are around 130 million. Okay? And in the future, so because of this known population, so we'll be able to determine so what would be the future population of certain countries. Okay, so there are a lot of applications, okay, so for growth and decay, and we'll try to cover some as we proceed with this discussion. So growth and decay problems so follow this rule, or follow this definition that the rate of change on the amount of substance is directly proportional to the amount of the given substance at any instant of time. So whether the problem is a growth problem or it's a decay problem, so it follows this definition, and we can transform this one into a mathematical relation wherein A corresponds to the amount of the substance at any instant of time. So therefore, the rate of change of this amount, okay, so with respect to time, is directly proportional to the amount of the substance at any instant of time. And since this is a variation, so we can convert this one into an equation. So by introducing a proportionality constant, K, so that would make it equal to K times A. And then from here, so that forms our differential equation. And from our differential equation, so we find its solution. So by integrating or by separating this one, so in this case, this is a separable equation. So we can change this or transform this into dA and then transpose A. So we divide it, and then K, so we multiply dt. And from here, so we can now integrate. So integrate, or the integral of dA over dt is ln of A, and is equal to the integral of k dt would be kt, and then of course plus the arbitrary constant c. Then if I want to express A explicitly in terms of t, so we can exponentiate both sides. So exponentiating both sides, so that will lead to E or A. And then so we can distribute, or we can express this one as e raised to kt, and then multiply it with e raised to c. It so happen that e raised to c, it's another constant, so I'm just going to write c again, and then e raised to kt. And that is the working equation, okay, so that we can use in solving growth and decay problem. So we just have to define that A so corresponds to the amount of the substance at any instant of time. And then we have two constants here. So we have the arbitrary constant C and the proportionality constant K. So those two constants so can be resolved or can be found, so as long as we have two initial values. Okay, so typically the arbitrary constant C so can be taken, that is when time is equals to 0. Okay, so when time is equals to 0, so we will be able to get what's the value of C. And then for the proportionality constant, so we need another value, so which is other than 0. So as long as we have another initial value which is other than 0, then we can find the proportionality constant k. So once we found the arbitrary constant c and the proportionality constant k, so we will reduce, okay, so our working equation so into an equation of the dependent variable a and the independent variable t, and thus we can solve problems, okay, so involving growth and decay problems. So let's have our first example. So it says that a certain radioactive element so follows the law of exponential change and has a half-life of 38 hours. So how long it takes for 90% of the radioactivity of the element to be dissipated, and determine the radioactivity that remains after 76 hours. So we have a radioactive element, and it says that it follows the law of exponential change. So that means so we use the formula that we had derived before because of the law of exponential change. But if it was if the relation, okay, statements so pertaining to the relation of the variables is given, then we follow, okay, so what was provided on the problem, and then we develop our own differential equation. But then in this case, so it was already mentioned that it follows the law of exponential change, so there's no need to develop our own differential equation. So rather, we can just simply use the formula right away that EA, okay, the amount of the substance at any instant of time, is equals to CE KT. Okay, then it mentions that the radioactive element has a half-life of 38 hours. So remember in chemistry that whenever we are given the half-life, so that means that is the time it would require. Okay? So the time it would require the substance or the original amount of the substance to be reduced to 50% of its original amount. Okay? So once a certain, let's say an element or a substance, so reduce its value to 50% of its original amount, then the time it would take that one is what we are calling as the half-life. So in this case, the half-life of the element is given to be 38 hours. So to resolve this, it would be better to figure it out, our given. So we write our given, and then initially, or by the way, so before writing that out, so we need to let, okay, so it's variable. So since we do not know the original amount of the element, but we're assuming, okay, or we're definite that originally, okay, so the radioactivity, okay, so on that element is 100%. Okay, so it's 100% radioactive. It just decays over a certain period of time. So I'm going to let R, okay, so to be the amount of radioactivity of the element. So the amount of radioactivity of the element. So originally, so when time is equals to 0, so when time is equals to 0, that is, so let's have A of 0. So that means when time is equals to 0, the amount of radioactivity of the element is 100%. Or it's just simply, it's a complete R. Okay? So that means 100% of radioactivity for the element when time is equals to 0. But then we are given the half-life. So we're in that would be 38 hours. So after 38 hours, so when we say half-life, so 50%. Okay, so the original amount will be reduced to 50% of its original value. So originally it's 100%. So therefore 50% of these, so would be 0.5 of an R. And these are the two given that we need. Okay, so in order for us to determine the value of C and the value of K. So we develop, or we get the value of C here, then we get the value of K here. So as to get our formula. So for our requirements, so it says that how long it takes for 90% of the radioactivity elements to be dissipated. So take note here that the formula A is equals to CE KT. So A here so corresponds to the amount that remains. So A is the amount that remains. Okay, so take note of that. So that means, so we are not concerned on the amount that dissipated, but rather it is the amount that remains. So that means, so for our first requirement, so if 90% of the radioactivity of the element dissipated, so that means 10% actually remains. So therefore, we are to find what is the time. Okay. So what would be the time? So when the amount that remains is 10% of the original. So 0.1 of an R. So next would be determine the radioactivity that remains after 76 hours. Okay, so 2 times of 38, right? So after 76 hours, so how much? Okay, so how much of the radioactivity remains? So for our solution, so again, so we use the formula A is equals to CEKT. But then we start with our first initial value, that is when time is equals to 0. So using this given, when time is equals to 0, A is equals to R. And then we substitute. So A is equals to R, is equals to C, E, K, then the time is 0. So from here, E raised to 0, so that is equivalent to 1. So therefore, C is actually equal to R. And now that we have R, so we substitute it to our original value or the original equation. So that is A is equals to, this time it's R, E raised to KT. So now that we know what's the value of C, so we proceed with our second given. That is when time is equals to 38. So our A so reduces to 50% of the original amount. So that would make it, so substitute A as 0.5 of an R is equals to R, E raised to K, our time is 38. So there are two R's on both sides of the equation, so we can eliminate them. And that's giving us 0.5 of is equals to E raised to, I'm going to interchange it, so 38K. So since we are finding the value of K, so we take the natural logarithm of both sides. Okay, so to move it down. So ln of 0.5 then will be equal to ln of E raised to 38K. Because remember, if we have, let's say, ln E raised to X, so applying properties of logarithm, this is the same as X times ln E. But then ln E is equals to 1. So therefore, that would just be simply X. So in this case, so we just eliminate the ln E. So it will just become, so ln of 0.5 will be equivalent to 38K. And to find K then, so we divide both sides by 38. So giving us ln of 0.5 divided with 38. And that's our value for K. So now that we have our value for K, so we substitute it in this given equation. Okay, so the equation that was created after substituting the value of C. So A then will be equal to R E raised to KT. So since we have K ln 0.5 over 38, I'll start it with T. Okay, so that would be T ln of 0.5. So divide it with 38. So A is equals to R E raised to T ln of 0.5 over 38. So this time, so this will be our working equation. It's a function, or it's an equation, okay, so which involves the dependent variable A and the independent variable T. So now, so since we were able to derive our working equation, so we can now find the requirements. So for our first requirement, so it says that when A is 0.1 R, so what would be the time? So when A is 10% of the original amount of the element, so what would be the time? Okay, so it would take, okay, so A is 0.1 of an R, then multiply it with R, e raised to T, ln of 0.5 all over 38. So we remove or we cancel out R, and then we can take the logarithm of both sides. So ln of 0.1 is equals to ln of E. So T ln of 0.5 divided with 38. So since ln E so can be is equivalent to 1. Okay, so and then applying the property, so that would just leave us T ln of 0.5 divided with 38. That's giving us 38 ln of 0.1, then divided with ln of 0.5, that is equivalent to T. Okay, so multiply both sides by 38 and then divide both sides by ln of 0.5. So giving us the time, so to be 38 ln of 0.1 divided with ln of 0.5. So A then, or T then, ln of 38 ln of 0.1 and then ln of 0.5. So that would give us 126.23 hours. So it would take 126.23 hours, okay, so to dissipate 90% of the radioactivity of the element. And for our second requirement, so our second requirement says, so what would be the amount of radioactivity of the element after 76 hours? So when time is 76, so what is the amount? So again, so our formula then, so A, our R, then E raised to T, so T this time is 76, so ln of 0.5, so divided with 38. So we input this one on our calculator, so that is just, we're just going to input E raised to 76, ln of 0.5 divided with 38. Okay, so E raised to 76, ln of 0.5 divided with 38, that is 0.25. Then we attach R. So R, so times 0.25. So that means after 76 hours, what remains, okay, on the radioactivity of the element is 25%. Okay, so from the original amount. Okay, so looking at the results, okay, so initially, when time is 0, the radioactivity is 100%. After 38 hours, so it reduces, the radioactivity reduces to 0.5%. And then we had computed that after 76 hours, okay, so it reduces even to 0.25 of an R. And then it took 126.23 hours, so to reduce it to 10% of the radioactivity of the given element. So as you can see here, as the time increases, okay, so as the time goes further, so the radioactivity of the element decreases, okay, or the element decays. Okay, so from 100% initially, so to 50% after 38 hours, and then to 25% after 76 hours, and then to 10% of the original amount after 126.23%. Okay, so the increase in time so corresponds to an exponential decrease in the amount of radioactivity for the given element. So this is a decay problem, and it follows the law of exponential decay. Okay, so that is our first example. It's about a decay problem. So you can always go back, okay? So with the equation or with the problem, okay, or with the video, okay, if you need some clarification. So let's have our second example. So second example, it reads that a bacterial population follows the law of exponential change. So again, so this is a growth and decay problem. I guess this is a population, so therefore it's a growth problem. So if between noon and 2 p.m., so the population triples. I'm not going to read the entire problem yet, so let's try to draw our given. But before that, so I'm going to so if between noon and 2 p.m. the population triples, so I do not know, so what would be the population? So I'm going to assume, so let's say p sub 0, so that means at time 0, so this would be the population initially. So this is the bacterial population initially. Okay. So for our given, so at 12 p.m., so which is the initial time, consider this the time. So we're going to designate that one as the time 0. So at time 0, okay, so the population, or at noon, okay, at 12 p.m., so I do not know the population, but I let it as P sub O, the initial population, and therefore, so A sub O, or sorry, A of, when time is 0, A of O is equals to P sub O, or P sub 0. Then at 2 p.m., so that means after 2 hours. So from 12 to 2, so it took 2 hours. So the bacterial population, so triples. So if at 12 p.m. that is P of O, so therefore after 2 hours that would be 3P of O. Okay, so 3P of O. So these are the two initial values that we need again. So to find for the value of C and K. So for our requirement, so at what time would the population become 100 times what it was at noon? Okay. So what would be the time? Okay. So we are asked by the time, and then when it becomes 100 times what it was at noon. So the population at noon is P sub O. So we are asked 100 times what it was at noon. So therefore, the population would be 100 of P sub O. And next, at 10 a.m., so what was the percentage of the bacterial population in terms of the population at noon? So at 10 a.m., so what was the percentage? At 10 a.m., so that means that is 2 hours earlier than 12 p.m. So since it is earlier, okay, so earlier than the reference time of 12 p.m., so therefore the time there would be -2. Okay, so that is 2 hours earlier than our reference time of 12 p.m. So that's A is, we are finding A when time is equals to -2. So for our solution, so we start again. So with our formula, A is equals to CE KT. Then initially, when time is equals to 0, okay, so our A is P sub O. So therefore, P sub O is equals to C EK times 0. So K times 0, that is 1. So therefore, C is P sub O. So we substitute, A then will be equal to P sub O e raised to KT. But then for our second given, that is after 2 hours, so when T is 2, so our A becomes 3 times of the original. So we substitute. So 3 p sub o is equals to p sub o e raised to k times 2. And p sub o, so will be cancelled out. So we take the natural logarithm of both sides. So ln 3 and ln e times 2k. So this becomes ln 3 is equals to 2k, and thus k is ln 3 all over 2. So we substitute it with the original equation, or with the substituted equation. So p sub o, then e. So we use this formula. E raised to kt. So we'll start with t. So that would make it t ln 3 all over 2. So p sub o, e raised to t ln 3 divided with 2. And this is now our working equation. So we start solving our first requirement. So that is when A is 100 times of PO, so what is T? So that is when A is 100 times of PO, so what is T? That is A is 100, PO is equals to PO E raised to T ln 3 all over 2. So PO will be cancelled out. So we take ln of both sides. So ln of 100 is equals to ln of E. So T ln of 3 all over 2. So this is the same as ln of 100, ln E. So we'll move out, which is equivalent to 1. So that would make it T ln of 3 divided with 2. So T then will be, so I'll move up 2. So it will become 2 ln of 100 divided with ln of 3. Excuse me. So T then will be equivalent to 8.38 hours. So T is equals to 8.23. Okay, so 8.23. Or sorry, 8.38 hours. So 8.38 hours. But then that's not the question. The question is, at what time would the population become? So 100 times what it was at noon. So we are asked the exact time. So since we are given 12 noon, so which is an exact time, then another given is 2 p.m. So this one is only 8.38 hours from 12 p.m. So what's the equivalent of these to an exact time? We can do this one manually, and we can use our calculator as well, so to transform this one into an exact time. So to do it manually, so we do it 8, okay, and then minus approximately 0.38. Or sorry, it should be 8.38, and then minus the whole number, because that is approximately 8 o'clock. Okay, so 8 o'clock. So 8.38 minus 8. So we have an excess of 0.38. So that means 0.38 or 38% of an hour. But then 1 hour, okay, corresponds to 60 minutes. So that's why we multiply 38 or the 0.38 to 60. So which is approximately 23.02. And again, so we subtract, so that would make it 8.23. And then we subtract again the whole number, so which is 23 minus 23. So to give us 0.02. That is 0.02 of a minute. But then 1 minute is equivalent to 60 seconds. So that's why we multiply it again by 60. and thus giving us the 1.01. Or in this case, that would be 1.01. And that would be in PM. So this is the equivalent. Okay? That is 8, 23, and 1.01 PM. But if we want to do it on our calculator, as soon as we get 8.38 hours, so you can always find this button. Okay, so the button looks the degree, the minutes, and the second button on your calculator. So look for this one. So this is usually beside the negative sign, the negative key on your calculator. So you can see there the degree, minutes, and second. By just simply pressing that one, so right away without doing the manual calculation, so you will get 8:23 1.01 PM. Okay? So that's how we do it if we are asked of the exact time. For the second unknown, so that is when time is -2, so what happens to the bacterial population? So that means this is earlier. Okay? So we are expecting if there would be 100% originally, so it should be less than the original amount. That is when t is -2. So what is A? So A then would be equal to P sub O e raised to -2. So for the time, then ln of 3 divided with 2. Okay, so T, this one, this formula, T ln 3 divided with 2. So thus A then will be equivalent to 1/3 of the original bacterial population. Or simply, A is in terms of percentage, so 33.33% of the original bacterial population. Okay, so that is example number 2. So this is a growth problem. So next problem. So radium decomposes at a rate proportional to its radioactive count. Okay. So I'm going to let R so to be the radioactive count of radium. And it decomposes. Okay, so this is a decay problem. So in 100 years, 100 units of its radioactivity decomposes to 95 units. So in 100 years, so 100 units of its radioactivity decomposes to 95 units. So that means after 100 years, so the 100 units initially, so decomposes to 95 units. So that means initially, so when time is equal 0, there are 100 units. Okay, so for the radium, or for the radioactive count of radium. And then after 100 years, so the 95 units, so decomposes to 95 units. So we have to take note of the preposition used, so which is to. So when we say it's to, so that means that's already the amount that remains. Okay. But if it was used instead of to, so it uses by, let's say by 95 units. So this one corresponds to Okay, after 100, so that would be 100 units minus 95, so which is equivalent to 5. So that's how we interpret it. Okay, so differently. So when it says 2, so that means it's already the amount that remains, okay, or the radioactive count that remains. But then, if it says that it decomposes by 95 units, so that means we need to subtract it from the original amount. Okay, so from 100, so minus 95, so that would be equivalent to 5. But in this case, it's 2. So therefore, we follow 95 units. Okay, so for our requirements, so how many units of radioactivity will remain after another 100 years? So take note of this, another 100 years. So that means there's already 100 years and then another 100 years. So what would be the radioactive count? Okay, so for the given, is that radium? Okay, so for radium. So originally there's a 100 and another 100. So that means, so what would be the radioactive count after 200 years? The second requirement is what is the half-life of this radioactive element? So half-life, so we're talking about the time. But then again, so remember that half-life is 50% of the original amount. So originally, we have 100% and 50% of 100 is 50. So that's why we have 50 here. And we proceed with our solution. That is originally, so this one, so when times equals to 0, A is equals to 100. So I guess you were able to notice this already, that when time is equals to 0 for growth and decay problem, our C is always the value of A, so which is equal to 100. Okay? So when time is equals to 0, whatever is the value of A, so that becomes our C. Okay? So that's for growth and decay problem. And thus, A then will be equal to C E, or sorry, it's 100 EKT. And then for our second given, that is when T is 100, so A is 95. So 95 then is equals to 100, so E raised to K times 100. So we divide both sides by 100, so 95 over 100 is equals to E raised to 100K. So 95 over 100 can be simplified as simply 19 all over 20 E raised to 100K. So taking the natural logarithm of both sides, so ln of 19 all over 20 will be equal to 100K. And K is ln of 19 all over 20 divided with 100. So that's our A then. So using this formula, 100 e raised to kt. That would be 100 e raised to t ln of 19 over 20 divided with 100. So that is our working equation. Okay, so let's now solve. Okay, so for our first requirement, so it says that when time is equals to 200, so what would be the amount of or number of units, radioactive units that remains? So that is when A is 200. So what is the when T is 200, okay, so when T is 200, so what is A? So that is, So A is 100. So e raised to 200. So ln of 19 all over 20 divided with 100. So the number of units then, so 200 ln 19 over 20 over 100. So that makes it 90.25 units. For our second requirement, that is, so how much time it would take, or what would be the half-life? Okay, so when A is 50 units, so what would be that time? So which is the half-life of the radium? So A is 50 equals to 100. So e raised to t, then ln of 19 all over 20 divided with 100. So dividing both sides by 100, so 50 over 100, that is 1/2. So equals to e raised to t ln of 19 all over 20 divided with 100. So we take ln of both sides, so giving us ln of 1/2 is equals to t ln of 19 over 20 divided with 100. So t then is 100 ln of 1/2 all over ln of 19 all over 20. So our time then, it will take 100 or 1,351.34 years. So to find, or for the half-life, okay, so of radium. And this one is another decay problem. So originally, so there are 100 units. After 100 years, so the 100 units reduces to 95 units. And then after another 100 years, so it reduces further to 90.25 units. Then the half-life, so that means 50 units will remain. The time it would take for that one to occur will be 1,351.34 years. Okay, so it took a lot of time. Next problem. So next problem is about carbon dating. Okay, so which is again a problem in chemistry. So there's a way on how to do it in chemistry. So this is a way on how to do it in differential equation. So it says that archaeologists so use pieces of burned wood or charcoal, so found at the site to date prehistoric paintings and drawings on walls and ceilings of a cave in Lascaux, France. So there was a cave in Lascaux, France, and then they found some paintings there on the walls and ceilings of the ceiling of the cave. And then the painting are and the painting that they use there, okay, so uses pieces of burned wood or charcoal, okay, so which has a carbon content. And they extract a sample, okay, so a sample of burned wood or charcoal, and then they found out that 85.5% of the original carbon-14, okay, so the original carbon-14 that was found there already dissipated. So that means only 14.5% of the original amount remains. It is known that carbon-14 has a half-life of 5,730 years. And then from there, so what would be the approximate years, okay, of those paintings? So based from the charcoal, okay, so or burned wood, so that were extracted from the cave. So I'm going to let and say C14, okay, so to be the amount of C14 that was found, okay, so during amount of C14 initially. Okay? Then we write our given that initially, so the carbon 14 is 100%. So when time is equals to 0, that would be 100% of C14. Then the half-life of C14 is 5,730 years. So that means 50% decays and only 50% remains of the original amount of C14. So we are just to find, so what would be the time of, or what is the, what's the time, okay, so to reach, so this is the approximate time, so since, or the approximate age, okay, so of those paintings, since the time the archaeologists so got a sample from the ceilings of Lascaux, France, or from the ceiling of the cave of Lascaux, France. So that is if 85.5% dissipated, so only 14.5 remains. So that means that is 0.145. Okay? So 0.145 of C14. So for our solution, that is when time is equals to 0. So A is 0.145 of, when time is equals to 0, so A is C14. So therefore, follow that C is C14. So A then is equal to C14 e raised to KT. And then, so when time, or after, or 4,730 years, so A reduces to 50% of its original amount. So that's, so A is 0.5 of C14 is equals to C14 e raised to K times 5,730. So C14 would be cancelled out. So ln of 0.5 then will be ln of E, so 5,730K. So K then will be, ln E will be, ln E is 1. So that makes it K to be ln of 0.5 divided with 5,730. So finally, our working equation so will be A is equals to C14 e raised to T ln of 0.5 all over 5,730. So finally, so when A is 0.145 of C14, so what will be that time? So this is the approximate age of those paintings. So A is 0.145 of C14 is equals to C14 e raised to, so T ln of 0.5 divided with 5,730. So this would be cancelled out. So we take ln of both sides. So ln of 0.145 and then ln of E raised to T ln of 0.5 over 5,730. And that's our K. So will be 5,730 ln of 0.145 over ln of 0.5. Sorry, that should be T, not K. So T then would be approximately 15,963.06 years. So again, so this is a prehistoric years. So that is 15 years. Okay? Almost 16,000 years. 16,000 years. And those are all problems, okay, so that we can discuss for growth and decay. So other problems is just a variation of these. And this is growth and decay, so application of first order differential equation. Good day and God bless.